Hi Paul, this is a quick video to try and address for me the points that you're raising. So I don't think I'll put this on the web. The question C seems to be a bit vague. Part 2 of the questions say simply doping requirements. The doping requirements of what? And hasn't this been covered by part A and B of the question? So part A is asking you to give a list of, so we are doing with question 1, yeah. The part A is giving you a list of things that you want to describe about intrinsic and extrinsic stuff. So for intrinsic silicon, you want to be talking about how whole pairs are being generated by heat, and these can move around, and you can then have a current going through. For intrinsic stuff, well, you want to talk about different types of intrinsic materials. So the N types, the P types, what they look like, how one of them gives you an excess of an electron and one of them gives you an electron take away, and how this means now that electrons can then move for an extrinsic material even at cool temperatures of the silicon material, by the fact that there's holes in the sort of the lattice system. So that's what A's ought to do about. So I can't see how that's got to do with part C. Part B is asking you to talk about what things are going to control stuff. So you could use it to create PN junctions. You could use it to control resistivity and conductivity and so on. So that's what part B is about. Part C is asking you to give a set of descriptions in terms of the materials. So yeah, you're right that you need to be stating there's P-type and N-type. That's given. So yeah, I suppose there's a bit of repeat there. You need to be talking about that you need to establish that there's going to be a junction, and you could talk a little bit more about the details of the doping. So how much doping that would be required in both the P-type material and the N-type material. And I think there's some diagrams showing that if you start to overdope the silicon, you get into problems. So you should be able to find a diagram like that somewhere in the textbook. So that'll be what they're looking for there. You want to be talking about, and we're still doing part C here, you want to be talking about reverse bias. So look up reverse bias in that part of the question, and you should be able to do that. And then the roles of diffusion and drift. Well, here you can talk about when you fuse the P and the N type together, how you're going to end up with this kind of diffusion of certain types of minority carriers and species from one side of material to the other side, and the how the electric field, when that's applied, that can then cause a drift of electrons. Then finally, conversion of photons to electric current. Just mention how the fact that when a light photon comes in and hits the material, that's going to create an electron hole pair, and that electric hole pair can then get swept past if you've the large. So we set up a situation, I think, don't we, where it's in reverse bias, and that electron hole pair will then get swept across, and then you can detect light. So that's what you want to do for C. So there is a little bit, I suppose, for A and B, but it's more describing those properties and under those headings. So materials, establishing the junction, doping requirements, how reverse bias behaves, how diffusion behaves, how drift behaves, how the photon current is generated. And that does, as far as I'm aware, can see how that really appears in part A, which is describing intrinsic and extrinsic type materials, and part B, which is talking about how the levels of dopants changes things in terms of conductivity, in terms of temperature and stuff like that. The only slight overlap is part B. You could say that this is what would be required to make a p-n junction. For your part D one, which you're struggling on, the first thing that you want to do there is to, I think you've got some data in terms of watts per meter squared. So this is basically giving me flux, energy flux. So the first thing I need to do is convert this into watts. So find your area, multiply it by this number, and then find how much watts that we're dealing with. So that's my starting point. So that is the kind of current that or is it current? That's the kind of wattage that I'm looking for. Now, what is watts? Watts is energy per second. So next guess is I need to find the energy for something. So you could use energy is Planck's constant times by frequency, although we are given wavelength, so we probably want to change the frequency to be Planck's constant speed of light divided by the wavelength. So from that I can find the energy of the particular photons that are hitting. Okay, so now I've got the watts requirement and I've got the energy requirement here. Now let's think of things. What's going to give me my biggest number? Well, if I take the amount of watts that I've got and divide that by the amount of energy for one particular photon, that will tell me how many photons per second I'm going to have arrive, so causing a potential amount of current. Now, unfortunately, not all of those photons will get converted to current, and that's when we're going to throw in our quantum efficiency. So we have decided that's how much photons is coming in per second. Multiply that by quantum efficiency, okay, and that will tell me how many of those photons get converted and generate electron hole pairs. Then each hole pair will generate one little bit of charge, so times it by one little bit charge for an electron. So therefore take that number there, multiply it by the efficiency, to multiply it by the charge, and therefore we will have the current. Okay, so that's what you need to do for that problem.